Okay, I think we're recording. So I've got the weekly announcements up here, and let me make sure I'm not on mute. Yep, got my. So I got the weekly announcements up. I just want to remind you that there's homework due this evening. It's our first real math assignments, a bunch of limit problems. I'm happy to talk about some of those questions at the start here. If you wanted to ask some of those, prepare to ask them while I finish saying a couple other things. It doesn't. I'll try to remember to put like a line item here about quizzes, but just know in general that we're going to have a quiz on Fridays. That's just the way it's going to be. That's one of the reasons I like to do it the in-person thing. And so just be prepared for that. And it's meant to be a low pressure quiz, low pressure assessment. It's mostly just trying to see if you're following along, right? It's open note. So it's just like, hey, with your notes in front of you, can you answer this question that looks a lot like the notes or the homework? Right? That's the goal behind those quizzes. So be prepared for that Friday. Just have your notes with you. If you have your notes, you'll be fine. And I usually do that at the end of class, kind of short, maybe 10 or 15 minutes, just to help me give you feedback. And I'll probably grade that through Gradescope. All right. Thoughts about questions about homework or anything before we get started? I don't want to ask any specific homework questions.
I had one.
I can barely hear you. Go ahead.
Oh, sorry. So I had a question about problem 2. So for me, it's the limit of sine of x over x as x goes to 0. So I plugged in 0. That came back as undefined.
Yep.
And so I made a table. And basically, once you get close to 0, it always returns the same value. But WebWork doesn't accept that value. So I'm not really sure where to go from there.
So we saw this one in the notes. Let me go ahead and show you where we saw that one. So I think that was the first one we looked at, if I remember correctly. Right, so I don't, unfortunately, that was when we wrote things by hand, but we did go over this limit in the notes. So what did you get when you plugged that one in?
It was a decimal of some kind. It's 0.01743453292.
I'm sorry, it's actually the second one, 0, right? If I remember correctly, I think the limit of this one was 1. Did anyone else do this problem? I wish I had my notes. I've got them right here. Let me look at it. Yeah, so we actually evaluated on this page. If you look at this page, we looked at sine x over x, and I drew a picture that had something like this. It had a hole in it at the point 1. So I'm not sure what you're getting when you plug that in. I guess maybe I would be sure that your calculator is on radian mode.
Okay.
But yeah, I mean, you could absolutely use a table for this one, but it's right in the notes, and I apologize that I don't have that. I have it right here. I guess I could show you what we did. I could also share this, but if you just this is posted on Blackboard. So if you just went and look at what we did on Blackboard, the answer is right there. I believe the answer should be 1. So just double check your calculator, and maybe we can look at it together if you're having a problem with that one. Yeah. So just for everyone who didn't see that, I would say check Blackboard for this. These notes are on Blackboard, and it has that answer. Other questions, other homework questions before we get started?
I had a question on number 4.
Let's pull up number 4. All right. What's your thought about number 4? So let me actually look at it quick. So we've got this piecewise function on this graph, and we are looking for limits as we approach -1. 0, and 2. Okay. So we're looking at like these 3 points, right? We're looking at trying to find this. What is the other one? 0 and 2. Thoughts? What were you thinking?
I just wasn't sure what they were really asking for because the 3 questions they were asking were worded weirdly.
So they're limit questions, right? So
Yeah.
this, oops, that's not the thing I want. I want this one. This first one is talking about the limit as x approaches -1 of this function. Right? As x gets closer and closer to -1, the function gets closer and closer to something. And I guess it's g of x technically.
Okay.
Right? This one is asking what's the limit as x approaches 0. This one's asking what's the limit as x approaches 2.
Okay.
And 2 of them have holes, and one of them does not have a hole. But either way, it's, you know, you're still doing the same process, right? So like the first one, let me erase these. This first one I'll do in yellow. That's like we care about -1 on that. And so we're walking along here towards -1 towards this point. And on the other direction, you're doing the same thing. So I would say this limit equals 3, it looks like. What's going on at 0, Mariana? What's the answer to the second one? Anyone help with this one? How do we do the second one? What's the limit as x approaches 0 on the second one?
Is that 5?
I see why you think it's 5, but each one of these things looks like 0.5, right? So from there to there is 1. So from here to here is also 1. So that would be 4.
Okay. 4 then.
Yeah. Right. You're approaching from this direction and from this direction. You're both approaching the same spot. Mariana, can I hear from you? What do you think about that?
I was just confused on what they were asking.
Okay. So now what do you think? So they're asking for the limit.
For when x is approaching 2.
Sure, that's the third one. Yeah. So what's going on in the third one?
Wouldn't it be 1?
Yeah, the third one will be 1. Because you're approaching right here, you're approaching this spot. That's it.
All right.
Oops. Questions at all? Anyone? Other homework questions?
I needed help on question 18.
I'm not sure who asked this one, but yours might probably looks a little bit different.
It was me, Harris.
Yours looks similar to this one.
Yeah, mine's x plus 10 minus 6, the square root of x plus 10 minus 6 over x minus 6.
And if you plug, and it's the limit as x approaches 6, I'm assuming.
Yep.
So what happens when you plug in 6?
You get 0 on the top and the bottom.
Right. So thoughts? What did you try?
I tried multiplying by the conjugate, but I think my math.
I think that's exactly the thing we should try here, right? You've got a square root plus or minus something else. So I think you should multiply by the conjugate, which is this. Oops, that should be a 10.
Sorry, the 6 on top should be a 4. The -6 should be a -4
Okay,
for the numerator.
gotcha. So that's multiplying by the conjugate. Does that look okay so far?
Yeah.
I think the key thing, just to point out for anyone who's confused, this plus did not change. This thing changed, right? It's just the thing between the square root and the not the square root.
I think that's where I made my mistake. I turned the plus inside of the square root to a negative.
Okay. Yeah, it's just the thing between the square root and not the square root. And I'm going to let you finish this one, but just to be clear, when you do this, I know I've said this a bunch of times, if you look at the notes, I always say this, but you need to distribute here, right? And you'll know you did it correctly when all of the square roots cancel out. So, and there's a couple like this in the homework, I think. So I'll just write the next step down. When you write this out, and I'm going to let you think about it, so I'm not going to maybe do the details. You can let me know if you want to see it, I guess. But when you do it out, you should get x plus 10 minus 10. No. Minus
Minus 16.
Right. Over this. Right, and then the top's going to end up being x minus 6, which will cancel out. So I'm just going to put a couple dots, dot, dot, dot. You'll eventually get x minus 6. And then those two things cancel, and then you keep going, right?
Yep.
Folks, see what I'm saying about this one?
Yeah. Thank you.
Other specific homeworks? Oops, I saw someone said something in the chat. Let me look at that. Will the quiz include limits, or will it just be on the intermediate value theorem? So the quiz is going to be on the homework. It's always going to be on homework that was just due, basically. So it's going to be on this homework that we're talking about right now, which does not include the intermediate value theorem. Other questions? Let's see how we're doing on time. I would like to get started here, but I'm happy to do something else. All right. So just remind everyone here, it's taken me a little bit to get things started. You know, we switched over to the iPad. I switched to Zoom, trying to figure out a method that works well. One of the reasons I switched to Zoom is because I believe it will do a nice job of tracking attendance and participation. So things like, did people say, you know, who put something in the chat, like who had their camera on and off. And so I'm hoping that this will help me take attendance. I just want to be clear that I am still planning on doing that. It's taken a little bit to sort of get in the process, but I think I'll be able to do that here. Okay. Anyway, no other questions. I'm happy to get started with the notes. Nothing else in the chat? Okay, great. Remind you too, I've got office hours this afternoon if you wanted to stop by and chat about the homework. I think that'd be a great idea. All right, so we left off, let's see, where were we? We were just finishing up limits. You know, we spent the entire class so far basically talking about limits, right? That's what we've been up to. And I know it seems maybe it's kind of silly, but we're going to finish this section by formally defining what a limit is. And I know they kind of feel like, well, didn't we already do that? And haven't we been using the definition of a limit this whole time? And the answer is yes, we've been using the definition of a limit. But what I'd like to do here specifically is talk about the very careful mathematical definition of what a limit is. And so this, definitions that look like this, that have Greek letters in them like epsilon and delta, so these things I'm highlighting right now, these are very, very common expressions in higher math. And what I'm about to show you is going to be a little confusing. I understand it is. I remember the first time I saw something like this, I was like very, very confused. And I really didn't start to get a handle on this kind of stuff till graduate school, to be perfectly honest with you. And so just know that this is going to be a little bit tricky, what we're going to look at. And know that this is not something that I test on. Okay, you'll never see something like this in a homework or on a test, but I'm going to present it to you in hopes that it shows you what advanced math courses look like. And if you're thinking about being a math major or the stuff interests you, you might consider taking some advanced courses. That's sort of the goal of what I'm about to show you. Some pretty abstract math. Okay, so let's look at the formal definition. So it says let's let I be an, and let me just clarify too. I'm going to try to relate this definition to the pictures down here to explain carefully what it says. Okay, so let I be some open interval around the letter C. In the picture down here, I is the interval on the x-axis, right? This is I. It's what's between the 2 points we care about, and C in this particular example is 4. So this limit as x approaches C equals L. What that means is that no matter what number we pick, so for any epsilon bigger than 0, there's some delta bigger than 0, such that if x minus C is less than delta, inside absolute value, then f of x minus L is less than epsilon. So in English, so not math terms, what this says is the limit exists if, no matter how close you want to be on the y-axis, you can pick some interval on the x-axis such that if you're within delta on the x-axis, you're within epsilon on the y-axis. And so just to kind of clarify a little bit further, this down here is the x-axis we're talking about, and this right here is the y-axis. Okay, so I'm going to draw some pictures on the graph down below to kind of illustrate what I'm talking about here. And let me also set it up top here. So the idea is you choose some distance delta so that if x, this is what I said in English, I'm just writing it down just so you can have it. So if x is within delta of C, the function output, I should say, is within epsilon of the limit L. So these are kind of like abstract general statements we make in math to say what a limit is. And let me take you into a specific example to kind of illustrate what it says. And epsilons and deltas are the common letters that are usually used. Okay. Can I clarify something about that? I mean, there's not a whole lot to clarify. It's probably confusing so far, but is there anything that people want to say so far? So let's use this concept to show that the limit of the square root of x as x approaches 4 is 2. And that's what's being plotted down at the bottom here. This is a graph of square root of x, and it's a visual representation of this limit, right? So first of all, we know that this is true, right? As x approaches 4, the square root approaches 2. And we know that's true because when we take the square root of 4, we get 2, right? So square root is actually a continuous function. And so we can just plug the number right in there. And we know that the answer is 2. But let's look at it carefully in terms of this careful mathematic definition. Okay, let's pick an epsilon. And in this particular picture, you can see that epsilon is being chosen as 1/2. And so we're going to go with that and work with that. So let's let epsilon be 1/2. So suppose epsilon is 1/2, 0.5. The question is, how close to x equals 4 do we need to be? Oops, only one E. In order for the square root of x to be within 0.5 of the value of 2. And I actually have a little applet here set up to show you what this looks like visually. And again, this is one of the more conceptually challenging things that I recall learning as a math student. And so the more pictures we could show to explain this, the better. I'm going to let people finish writing this down before I share my screen and show this applet. And again, that's kind of what's being shown on the visual here, right? Epsilon is 0.5. Well, I'll come back to that in a second, actually. Let me let you finish writing that. All right, just kind of looking here. Looks like most people finished writing. I'm going to share my screen. Of course, I can't see everyone, but I'm going to go ahead and assume everyone's all set. Let me share my screen and show you this applet of the situation. Is this working? Doesn't really seem to be working. Okay. So here's the situation, right? This is the square root of x. This is just a graph of the square root. And we are looking at the limit as we're approaching 4, right? So c in this case is 4. Notice how when I put a 4 in here and I hit enter, it puts a bracket around the thing we care about, right? And then the limit we know, because square root of 4 is 2, and so that's going to be 2. And notice when I put 2 in there and I hit enter, it puts a bracket around the y values, right? So the c are the x values, as I mentioned. L are the y values, it's the output. And you can see there's sliders up in the upper left-hand corner here for epsilon and delta. And so the idea is, and notice how when I slide epsilon, let me go ahead and slide it a little bit. Uh-oh, come on, internet. When I slide epsilon, it makes that thing bigger or smaller, makes the space bigger or smaller, right? And when I slide delta, it makes the other one bigger or smaller. So let me make this one really small just so it kind of gets out of the way. The question is, let's say we want to be within, in this case, it only goes up to 0.4. So let's say we want to be within 0.4 of the limit, right? So I made epsilon 0.4, and it's now made a bound around the y values between 0.4 less than the limit and 0.4 above the limit, right? So if you look over here on the y-axis where I'm kind of showing you with my cursor, this lower point is 1.6, right? Because it's 2.4 minus 0.4. And this higher point is 2.4, because we're creating a buffer of 0.4 around the limit, right? So if we want to be within this close in the y value, I'm going to extend the delta now until it matches up with the endpoints. And this is too big, actually. I need to make this slider bigger. Can I make this slider bigger? Can't make it bigger. So let's make this one smaller. Let's say we want to be within 0.1 instead. Let's make it 0.2. Can I get that close? No, I can't. I got to get even smaller. Let's say we want to be within that close. All right, so the biggest point that it hits right here on the graph is right here, where I'm kind of showing you with the cursor. And the smallest point is right here. And so I'm going to make delta bigger until it hits those two values. All right, so I'm hitting it until it hits those two edge values. And it looks like I have to extend it all the way to 0.4 to make that happen. And so what we just learned is I need to be within 0.4 of 4, right, of x equals 4, in order for the output to be within 0.1 of the limit. And if I want to get even closer, right, if I want to make epsilon even smaller, then that means delta needs to get even smaller as well, right? If I want to get closer, then this needs to get closer. And so every time epsilon gets closer, delta needs to get closer. It's basically saying, how close do I need to be around the x-axis in order to make us this close around the y-axis? And so I'm going to switch back to my iPad in a second and show you that on the graph. Does anyone want to say anything about this picture? I'm going to draw the same, basically the same thing on the graph in a second. Let me go ahead and stop sharing and do the same thing on my iPad here. So back to our image. There we go. If we want to be within 0.5 of the output, the question is, how close do we need to be on the input? Oh, give me 1 second. I just accidentally closed this out. Oh, I closed that one out too. That wasn't a good idea. Right? Yeah. Okay. So what we want to do is we want to be within 0.5 of the limit, right? So over here on the y-axis, is this following? Yes. This is the epsilon part, right? This is taking the limit above and below the output, right? And so the question is, if we want to be within this range, and let me go ahead and highlight it with red, right? If I want to be somewhere within that piece of the graph, right? If I'm somewhere on that red line I just highlighted, I'm within 0.5 of the output of 2. The question is, where do I need to be on the x-axis, right? Well, very clearly, just looking at the picture, I need to be between this location, right, and this location. And so if delta is somewhere in here, then the output is going to be somewhere within that range. That's sort of what we're trying to say. But let's say it mathematically. Let's say it carefully mathematically. Right? And I'm going to draw a line down the middle of the screen here because we're going to split this up into two different things here. Okay. So let's pick our epsilon to be 0.5. If we want the output to be between 1.5 and 2.5, the question is, what does the x value need to be on? Well, that means the square root of x needs to be between those two numbers. Right, so we just kind of, from here to here, we know that, let me do that in another color. From here to here, we know that y equals square root of x. So I just substituted in square root of x. So we want the y values to be between 1.5 and 2.5. Well, the y values are achieved by square rooting x. Okay, so now we want to just figure this out. So let's square both sides. So from here to here, we're going to square all the terms because we're trying to get a condition on x, right? And so if I square everything in that expression, it becomes 2.25 is less than x, which is less than 6.25. So I just squared everything to get rid of the square root. And what this says is, as long as x is between 6.25 and 2.25, our output is going to be between 1.5 and 2.5, which is what we were trying to figure out. Okay. And so let me just figure out what delta is then, right? So I want to be between those two numbers. So let me go ahead and label that actually, right? This right here, what we just figured out, this is 6.25. And this point right there is 2.25. But what does delta need to be? Because we want to create like an even interval on either side of 4. And that's not an even interval, right? It goes up by 2.25 in one direction, but only goes down by 1.75. In other words, what I just figured out, just kind of looking at that picture and thinking about this, 4 minus 2.25 is 1.75, right? That's going to the left. 6.25 minus 4 is 2.25. And so if we want to make sure we're inside that correct range, we want to choose the smaller number. And so based on those two things, 1.75 is smaller. And so that's going to be our delta value. In other words, what all this has what we just figured out based on all this information is that if x is within 1.75 of x equals 4, then the output, in other words, when you square root it, that's what you get when the output happens, right? Then the output will be within 0.5 of the limit. Kind of relating it back to the definition at the top there. That's what we would say in words. If we wanted to say that mathematically, i.e., what we would say is if x minus 4 is less than 1.75, right? That's our delta value. Then the square root of x minus 2 is going to be less than 0.5. That's our epsilon.
It cuts off slightly. I can't read the bottom there.
What are you using? Using a computer? Just curious. You on a computer, Gregor?
Yeah.
What's the last thing you see? Because I see it on my screen. I'm just trying. It'd be helpful to know where it cuts off.
I see IE, and then the rest of it just cuts off.
Okay.
So that's good right there.
Yeah, by all means, let me know if that happens. I'm keeping an eye on my own screen, and I can see it on my screen. I'll always be sure that I can see it, but obviously I'm not able to see what everyone sees. I think there's some weird thing that happens between computers. Anyway, formatting. Can I ask you some questions about this? We're going to do this in general in a second. So we're going to actually make this more careful and more general than it already is. I've picked specific epsilons, right? I'm saying I want to be within 1/2 of that limit, and what I just determined is if I want to be within 1/2 on the y values, then on the x values I need to be within 1.75 of 4, which is, maybe that's interesting or whatever. But what we want to do is we want to say how close we need to be no matter what epsilon we choose, and so that's what's going to go in this sort of blank space that's currently open. Is an even more generalized version of what we just did. And again, this isn't something I'm going to test you on. I'm hoping that math majors or people who are interested in thinking about things abstractly might be interested in this, and it might encourage you to take some more math courses or come talk about it or whatever. Just giving you an idea. Like if this was a course where it was only math majors in it, we'd be digging into this kind of thing pretty deeply. But since this is a course it's a general education course, it covers lots of different majors, we usually kind of skip over this in our school at least. Anyway, questions before I sort of mention this in general now? All right, let's make it super general. So again, I chose on this last one, I didn't choose, I took it from the textbook, but the textbook chose epsilon to be 1/2, right? So it sort of set an interval around the limit. Let's make an arbitrarily small interval. So let's let epsilon be some really small number. So let's epsilon be positive, but think about it as a really, really small number. So we want to get really, really tight. We want to get infinitely tight around that limit is the way to think about that, but still some interval. And so in general, what we want to do, we know the limit is going to be 2, right? And so we want the difference between the output and 2 to be as small as we want. Right, so when you say let epsilon be bigger than 0, and you say it could be anything, and then you write down y minus 2 less than epsilon, that's saying we want to be really, really close to 2. All right, let's do the exact same thing we just did a second ago. So this absolute value expression that we just wrote down, if you remember back to pre-calc, that changes into this expression. I'm not going to go into detail about that. Hopefully you remember that. That's just the definition of absolute value. Well, we know that y equals the square root of x, and so we can just substitute in square root of x. Let me add a couple of these things. So here to here, it's the definition of absolute value. From here to here, we just let y equal square root of x. Let's keep going. We're trying to do the same thing, but instead of having numbers in here, I'm just going to leave epsilons and deltas, right? So let's get x by itself in the middle there. So I'm going to add 2 and then square both sides. Or square all sides, I guess I should say. All right, so just added 2, so everything gets a +2. And then when you square it, it gets rid of the square root. And so this is the sort of the analogous stage as we were a second ago right here, right? Those two things I'm connecting with the red line. we're sort of saying as long as x is between these two values, then the output is going to be less than epsilon, except on the left, what we did first, that's specific numbers. On the right, it's in terms of epsilon. So when you pick an epsilon, it tells you how close you need to be. You see that? So pick an epsilon right here and right here, plug it in, add 2, square, and that would tell you the interval around x that you need to be in order to be that close, right? So let me keep writing this down. Let's keep going. So let's square this out. We'll square out the epsilons, and let's get even more specific. So when I square that out, I get 4 minus 4 epsilon plus 4 is less than x, which is less than a very similar expression. Now let's factor, right? This is almost the same thing. We've got 4 plus or minus something. And let's factor out a -1. And so this is the same thing that looks like this. Yeah. No, that's not what I wanted. I messed this up a little bit. This should be an epsilon squared. Sorry, I can't read my own handwriting. And so then this becomes epsilon squared. Yeah. Right. So all I did is just factor out a -1 because I wanted it to say 4 plus something and 4 minus something. So it's telling us, it's saying like, if you want to be at 4, you need to be a little bit to the left. This is telling you the left part, right? And then a little bit to the right. This is telling you the right part. And again, it's in general. We don't even know what epsilon is, but you pick an epsilon and then it'll fall out. In other words, let me sort of write a sort of takeaway thing. Since epsilon is any positive number, 4 epsilon minus epsilon squared is actually less than 4 epsilon plus epsilon squared, right? In other words, when you subtract a positive number, it's less than adding a positive number. And so that's the smaller one. And so that's our delta then. And so that means delta has to be less than that expression. If that happens, then we will be within epsilon of the limit. This is sort of this is the takeaway, so I'm going to box it in a little bit. And so notice how epsilon's any positive number. So on the left, it could be 0.5, right? So we let it be 0.5 here, but it could be any positive number. It could be 0.1, it could be 0.01, it could be 0.001. And so as epsilon goes to 0, right, the delta value goes to 0, and we get closer and closer and closer to the number 4. Right? So this is a generalized way to write down it's what's called the epsilon delta proof of the limit. That's how people often refer to this kind of thing in math. I would love to talk about this a little more if people have some questions or comments about it. Again, I know it's not the most easy thing to understand, and after this page, I probably won't ever return to this. But if this is the kind of thing that's like, oh, that's kind of cool, I see how you're generalizing that, and I'd like to learn more about it, then that's why I'm doing it. I hope you take some more math classes. That's sort of the thing you should think about. Or I could help direct you if you wanted to think about that. Can someone say something about this? Ask a question about it. Love to hear general thoughts.
It actually does kind of like break down like the idea of a limit more easier.
I've never heard that, but that's really nice to hear. Thank you. Yeah, sometimes I worry that this confuses people. So sometimes it helps hearing like, oh, that actually makes sense. And if it does confuse you a little bit, that's okay. Look, because it's a confusing thing, to be perfectly honest. And just know that this is, we're just breaking this down into more and more abstract ways to think about it, which is what we end up doing in math. We think about things extremely abstractly. And this thing I boxed in at red at the bottom here, right? This thing right here is as abstract as it gets, right? You pick how close you want to be on the y-axis. You pick an epsilon, and it'll tell you how close you need to be on the x-axis to get that close. Even if there's a hole there. I want to remind you about that too, right? This example we looked at is the square root, and it doesn't have any holes or discontinuities or any weird stuff. So that's an easy one, right? What I've just shown you, though, works with complicated, weird functions too, is kind of the powerful thing about that. Thanks for that comment. Other questions or comments?
Also something to add on. I don't understand like why there's a smaller side and a larger side of epsilon.
Yeah, so the idea is like, if I just zoom in on this picture a little bit, if we want to be between here and here on the y-axis, because this line, it kind of looks straight, but it's not straight, right? It's curved. It's square root of x kind of has like a curved shape to it. And so if we want to be between those two lines I just drew in red, then we want to be between these two places on the x-axis, right? But that's not an even interval around 4, right? Like, in other words, this distance right here, and that I just did in green, is less than that distance. One of them is like 1 point, and you can, oh, it actually says right there, right? One's 1.75, one's 2.25. And so we want to pick a specific interval that's even around 4. And so if we want an even interval, we want to make sure we pick the smaller number, because that'll make sure we stick inside the blue lines I just drew, right? In other words, if delta was 2.25 instead here, that's okay on this end because it would align there, but over here it would be over outside, and then we'd be outside the region up there. Does that make sense?
Yep.
So we picked the smaller one just to make sure that the interval is inside of what we're trying to achieve, right? We want to be somewhere between there and there. And so that means we want delta to be the smaller one. And so I guess then that means this doesn't happen, right? It doesn't hit there. It actually hits a little bit before there. It'll hit at 5.75. And we'll actually be up here, which is fine because we're still inside that zone. Yeah, that was a good thought there. That shows that you're definitely following along with this argument, I'd say. And that was just for the specific example, right? For the general example, it was a little bit more tricky. We have the same kind of thing where we were looking at like 4 plus or minus something. Let me zoom out a little bit so you can see it all. Right, that's 4 plus something, 4 minus something. And I was trying to figure out like, which is the bigger one? And it turns out, since epsilon's positive, that when you take something and add a positive number, that's going to be bigger than taking something and subtracting a positive number. And so that's how we figured out which the bigger one was. And that's why we used the smaller one. Yeah. Smaller. Other thoughts? Thank you for that thought. Okay, if you hated that, that's okay. Just push it out of your mind and we'll move on to the next thing. And it's very rare in math where I can say something like, you don't really have to worry about this too much, because usually it builds on itself, right? But this is something that we're not going to build on, and I would just encourage you not to worry too much about it. But if you're interested in it and you want to figure it out, come talk to me. I'd love to walk you through it more carefully. All right. Let's move on to continuity. So this is starting homework that's due next Wednesday. Okay, not everything we've done so far is in the homework tonight. This is going to be in the homework next Wednesday. And so we're starting to move into the idea of continuity, which you can see involves limits and function values, right? So we're building on the concept of a limit. So we want to understand what a limit is. In order to do this, so let me know if you need some help. Excuse me. So this says a function is continuous at a point C if the limit as x approaches C equals the function value at that point, right? So f of c is the output at that point. And so this is the definition of being continuous at a specific point, x equals c. And the number 2 is telling us continuity on an entire interval, right? So the first one's how do we know if we're continuous at a specific point? And the second one is telling us how do we know if we're continuous everywhere? And so being continuous everywhere on a specific interval means being continuous at all the points on that interval is what this says, right? So it says f is continuous on an interval if every c in that interval, it's continuous there, right? So this is just the definition of continuous on an interval. It's just an extension of being continuous at a point. Practically speaking, the word continuous means what you think it means. Like if I showed you a bunch of graphs and I asked you, without knowing anything else, which ones are continuous, you would probably be able to answer that question without knowing the formal definition, right? It just means you can trace your finger along the graph without picking it up. So on this picture right here, it'd be helpful if you looked at the screen. On this particular graph, there's a hole right there, right? That's a hole. And so it's not continuous there because if I were going to walk along this graph, I would need to pick my pen off the paper and jump over that hole, right? So it's not continuous at that hole because if I were tracing my finger, there's a discontinuity, right? You have to jump over something that's not there. And so again, practically speaking, you should already kind of know what continuity means. What we're going to spend some time on is the careful mathematical definition. That's what we always do in math. And so this definition really implies 3 things. Okay, and that's what it says. A useful way to establish whether or not a function is continuous is to verify these 3 things. So we need the limit to equal the function value. So that implies, number 1, that the limit exists. Number 2, that the function is defined at that point. And number 3, that the function value equals the limit, right? So this statement that I'd boxed in blue actually has 3 implications to it. Actually 4, really, if you think about it. Because if you want the limit to exist, that means the left-hand limit and the right-hand limit have to both exist and equal each other, right? So this subpoint actually has like 2 hidden implications inside it itself, right? So that's what we spent the last week or so looking at, is these left and right hand limits. So we need the limit to exist. So the right hand limit equals the left hand limit. The function value needs to be defined. That's hopefully self-explanatory. There needs to be a point there. And the limit needs to equal the function value. So number 3 also implies that 1 and 2 are both true. They both exist and they equal each other. And I'm purposely trying to leave a bunch of room here because down here we're gonna write a lot of stuff down there. So try not to go into that zone too much while you're writing. Okay. Let everyone write that down. Can I clarify something about that definition? The 3 or 4 things on this page, 4 things, are gonna look at some of these examples. And we're gonna go kind of carefully into each one of those definitions. Can I clarify anything about that before we do? Okay. Looks like people are caught up. So the question here, like you said, or like it says on the page, it says, on what intervals are the following functions continuous? And so we want to look at these 3 things. I'm going to box it in because these 3 things are going to come back and we're going to look at it a lot. We want to look at these 3 things and think about which, if any of those things, are violated anywhere, right? So the first one is just a picture. And then we're going to look at 3 functions. And we should be familiar with these, right? We've actually looked at least 2 of them already. So I don't know. Does anyone want to say anything about the graph there? Right. So we're looking to see whether or not limits exist, whether or not the function is defined at the location, and the limit needs to equal the function. And so this is a really simple graph, and it's 3 pieces, but they're all connected except at the hole. So can someone just take a stab and tell me where this thing is not continuous?
At 1, 1.
Yeah, at the point 1, 1, right? When x is 1, there's a hole, and so the function's not defined, right? So in other words, f of c is not defined at the hole, and so that's going to be the problem. But we need to be we want to carefully write this down mathematically, okay? So I'm going to go through each one of these steps, 1, 2, 3, each one of those conditions, and sort of talk about them one by one. And I'm going to start up here just so I have enough room. So as we approach c and any points in this interval of f of x, it's going to exist for every point on the interval 0 to 3. Right, anywhere in the middle there, the limit exists, even at the hole, right? Even at the hole, the 2 sides are coming at the hole and they're approaching the same location. So does everyone agree that the limit as x approaches any point exists in this interval? And notice how I'm not including 0 or 3 because I've got parentheses around them. Is that okay? Okay, what about the function value? Number 2 says the function has to be defined at the location for it to be continuous. So the function is defined everywhere on that picture except at 1. Right, so f of c, let me do it in another color actually, just so it stands out a little better. F of c is defined for all c in the interval 0 to 3. Those are x values, right? Except when x is 1. And so right away, we know it can't be continuous at 1 because number 2 is violated, right? F of 1 does not exist. That's what I'm trying to say, because there's a hole. And so this means the function's not continuous at 1. So since condition 2 fails, this function is not continuous at 1. So okay, so if this is a test question, I would say something like either tell me where this is continuous, or I would say something like tell me why it's not continuous at 1. And you would say something like, well, all the limits exist, but the function's not defined there. Thoughts about that? I'm going to add one more point here about questions so far. So just kind of looking at the third point then, if this is a test question or something, you can just stop after you show me why it fails. But just kind of looking through the third point says all the limits have to equal the function value. And so that's true at every point in this interval except at 1. Right? So the limit as x approaches c of this function equals f of c for every single point except at 1. Except at x equals 1. And it's only because f of 1 doesn't exist. right? It's possible actually for this function to look like this. It's possible for there to be like a rogue point just below the hole. And so f of 1 could exist, but it wouldn't equal the limit, right? I'm trying to clarify that with this thing right here, right? If this was what the graph looks like, then we would say condition 3 fails, not because the function is not defined, but just because it doesn't equal the limit. So there's just a slight difference there in that case. Right? But since it's not there, we say it doesn't exist.
I got a question.
Yep.
So does that mean every time there's a hole in the function, it won't be defined?
So what I'm saying is there could be a hole like that, but sometimes maybe the point's down here. And so if it looked like this, then f of 1 would be 0.5 because the hole, right, you would go like to that point. So there are graphs that exist where there's a hole and then there's a place to find right above or below the hole.
Okay.
Most of the time that doesn't happen. I'm just saying it's possible for that to happen. Other thoughts? And I guess to clarify further, the thing I'm trying to clarify here and point out is in this situation where there's just a hole and not a point, condition 3 fails because the function doesn't exist. And what I was trying to say is if there was a point there, we would just, instead of saying because the function doesn't exist, we would say because f of 1 does not equal the limit. And I'm just trying to differentiate between a couple of slightly different scenarios, hoping that it illustrates the point. Questions about that? But again, that's only if there's a point right there. There's not a point here, and so we would just say it's because the function doesn't exist there. And then the final answer is where it's continuous, right? So the question is, on what intervals is this thing continuous? What we just showed is that it's not continuous at 1. And so the answer is it's continuous everywhere else, right? So the final answer here would be, based on everything that we wrote down, that this function is continuous on the following x values: 0 to 1, 1 to 3. And so when you write something like that down, it means not 1, right? See how we're skipping over 1?
Professor, I just got a quick question.
Yep.
How come you don't include those points? Why are they not the brackets? Why are they just parentheses?
Yeah, so we put it in the middle around the 1 because we want to avoid that point, right? We're like getting really, really close to 1 on the one side and really, really close to 1 on the other side.
Mhm.
We don't want to put 1 in. The end points, these points don't get included.
Why is that?
Well, why do you think? Or why does anyone think? Because one of the conditions fail. One of these 3 conditions up on the top fail for that.
So for it to be continuous at that point, it has to have values on either side of it, right? So if it's the end point and there's nothing after or before it, then it's not continuous there, right?
Yes, exactly. But what is the issue? Which one of these 3 things fails? You're exactly right, but take it a step further and say which of those 3 things actually fails. So let's just look at 0, for example, right? Let's look at the point on the left here. We need these 3 things to be true for that to be continuous at that point, but one of them fails.
Isn't it missing the limit from the negative direction?
Yeah, it's missing this left-hand limit, right? There's no graph over here to approach that side from. So it's kind of like a special case, or maybe you would call it like a special rule or something. But there's no graph to the left of it, so the left-hand limit couldn't possibly exist, right? It's kind of like a special scenario. I almost tried to write that down actually, but I was running out of room, so I just decided not to. But I'm glad you brought that up. Does that clarify it?
Yeah, that's good. Thank you.
and again, that's like a special case thing, not the kind of thing I would try to trick you on or something like that in a test or anything. Other thoughts? What are we doing here? 12. Okay. Let me double check my calendar real quick. I'm gonna try to stop here. I'm gonna try to be more careful about your time. One of these sessions is supposed to be 50 minutes, so I'm not probably gonna do that. I'm just gonna try to keep the sum of both the Monday and Wednesday classes to within whatever it needs to be. 125 minutes, I think. Right? Yeah. So like if I use 60 minutes here, maybe I use 65 on Monday or something. Anyway, I think I went the full period Monday, so I'm already over. So I should stop. But the other thing I'd like to do is I'm available till 12:15. And so I'm going to sort of try to stop at certain places. But I'm happy to stick around too if people have homework questions, I guess. That would be another good time to sort of talk about homework. So I'll stop right here at this continuity, and then we'll look at some examples with functions on Friday in person, right? Friday's in person. We'll have a quiz as well. So make sure you bring your notes with you. Open note quiz, trying to keep it low pressure, but if you don't have your notes, it's going to be higher pressure. Questions about anything? Does anyone want to stick around and talk about some homework? So you're welcome to leave if you want, but if you want to stick around, maybe shoot me a question.
Quiz is just on limits, right?
Just on limits, yep.
Okay, thank you.
So I see Kim asking about problem 5. Which one is it? Probably that one. Okay. So the first thing you should realize is these two questions help you answer the third one, right? You do the left-hand limit, the right-hand limit, and then you use those answers to answer the third one. If they're equal, you get an answer. If not, it's a DNE. But the fourth one, the limit as x approaches 0, is not providing that for you. So you need to look at the right and left-hand limits yourself and see whether or not they equal each other. Right? It's not asking you to enter that. You need to do that yourself. So on 2, or I'm sorry, when we're approaching 2, right, we're approaching x equals 2. And when we approach it from the left, it's like this. And we approach it from the right, it's down here. One, two, three, 4. So I agree in your first answer, but what's the second answer?
Should be 2.
Should be 2. And what about the third answer then, based on that?
Well, they're not equal to each other.
Right.
So would that not exist?
So that does not exist then. Right, they need to be approaching the same spot from both sides.
Okay. So I was looking at sometimes I get confused of which one, like which line to look at, I guess. I'm still really bad at figuring that out.
So I would say, on this one, if we're looking at 2, maybe it would be helpful, I don't know, to draw this, or just right, we're looking at like this spot right here, just kind of having your eyes focusing towards that spot from either side.
Okay.
And then that helps you pick which piece of the graph to look at then. I don't know, that's just a suggestion, I would say. What about as x approaches 0?
If you approach it from the right hand side, would it, there's an open hole at 0?
So the open hole just means that g of 0 goes to here. That doesn't really have anything to do with the limit necessarily.
So would that one be at 4?
The left-hand one or the right-hand one?
The left-hand one.
Yeah, so this right here is a left-hand one, and so that would be 4. What's the right-hand one?
The right-hand one would be 0?
Yep. And so those do not equal each other.
So that one would also not exist?
Yes.
Three. Okay, and then the bottom one would g of 2 would be 3.
Yeah, so that right. When you go up here, you don't go through there, you don't go through there, you go to the filled in circle.
Yep. Okay, I got it right. I submitted the answer.
All right, great. Guys, got some other questions? Kyle, John, Tayshawn, Jorge, Gregor?
Yeah, I could use some help with problem 1. Hopefully it's just an easy, something easy that I'm just missing.
So this is like getting you to plug in values in a table, right? So the thing on the left is the right-hand limit, and the thing on the right is the left-hand limit. I know that's a little confusing, but right, these numbers, so you're evaluating the limit as x goes to 3. These ones here are approaching 3 from the right, and these ones are approaching 3 from the left. And what numbers are they getting closer to?
3.
3.
I tried 3 and that did not work.
Oh, yeah. Okay. I got confused by this too. I am absolutely getting confused, probably for the same reason you are. Let me do this again. So these are the x values, right? We need to actually plug them in. We need to plug them into the function to get values in here.
Oh, yeah. So.
And you don't even necessarily need to do these values, right? It's just sort of giving you a hint. I would just plug some numbers in a little bit bigger than 3, a little bit less than 3, and then see that you'll see that they're close to 4.5. So I maybe this is what you think. When I was originally looking at this, I was thinking this was the output, but these are the x values, right? So these things are like plugging some stuff to the left and to the right, and the question is, what is the function value up here?
For which one?
You got to plug them into here.
Yeah, right. So it's asking for the limit as x goes to 3 is 4.5, I guess, but I just plug 3 in and I get 4.5. Is that how I was supposed to do it?
So it looks like well, you can't plug. If you plug 3 in, you'll get 0 over 0 on this one.
So
right, so like you would do 2.9 cubed minus 27, 2.9 squared minus 9. That would tell you something to put in one spot. Then get a little bit closer, 2.99. Oops, that should be squared. But you'll see the numbers getting closer to 4.5. Should we go back to the notes quick here? Oh, I don't have these notes though because it's the first thing we did. Right, it's what we did right here. We made a table. You pick some numbers a little bit less than the limit, a little bit more than the limit, and you plug them in. I feel like you get this stuff though. So what's confusing about that?
I really don't, honestly. Like, the way the question's worded, that's just what threw me off. I don't know.
I mean, it's worded the same way it is in the notes, though, I would say, right? We made a table to estimate the limit. So do you know what to do? Are you still confused? Can someone else help me? Maybe I'm missing something.
I don't know. I guess I'm all set.
It doesn't sound like it. That is not a good thing to hear. Do you understand? I mean, you understand the concept of making a table, right?
Yeah, I understand like how it gets bigger on one side and when it's small on the other.
Yeah, great. So 3, we're picking some numbers over here. We're picking some numbers over here. You need to plug those numbers into the function to see what the output is. So all these numbers get plugged in here, and then you fill in the table. Right? All these numbers go in there, and then you fill in the table.
Okay.
And you'll see that the numbers are getting closer and closer to 4.5 in both cases.
Now I see.
Okay.
Yeah. Thank you.
What else? What else are you guys looking at? Kyle, got something? Anyone?
I mean, I guess if no one else is gonna ask, I'll ask help with 7.
Yeah. What'd you say? 7?
Yeah. Am I just plugging in -4 into it, and then
Yeah.
if it gives me 0 over 0, is that does not exist?
I don't think it should. So no, if you get 0 over 0, that means you need to use one of the techniques we have. But I think you can just plug 4 right into this one.
-4, right?
-4, yeah. It's going to be some fraction. And then raise it to the 4th power.
Would the answer be 0.13 for that?
You said you cut out. Can you say that again?
All right. Would the answer be like 0.13 for that?
I don't know. So you got?
Just a second.
It should be 002. Did you raise it to the 4th power?
I'm doing that right now. I'm trying to figure out how to do that on my calculator.
Yeah, I did.
So when you plug in 4, you would get 1 minus -8, -4, that is. And then you get 1 plus 32. All right. Is this what you got?
Oh, 32. Dang it.
That is not correct. What's going on here? To the 4th power. Oh, that's why. Yeah.
So it's -7/30. Oh my gosh. I'm just running into super mistakes.
I would just enter it like this too. I don't know if you're trying to get a decimal or whatever, but just enter -7/33 to the 4th. I think that's the easiest thing to do. Sometimes WebWork likes different numbers of decimals, unfortunately. It's not something I can control. And so instead of trying to get a decimal, if you just enter the fraction, it's usually your best bet. I don't know who said they got 0.13 for this. Was that Kyle? But does that look okay? Maybe Gregor.
All right. Sorry about that. I was just having calculator problems, but I got it.
Great. I'm going to take off unless you guys got another question.
Thank you, Professor. Have a nice day.
You're welcome.
Thank you. What are your office hours today?
3:15 to 4:15.
All right. And they send you.
All right, bye.